college chemistry. Today we're going to talk about Hess's Law Lab, Lab 6.3. And what I'm going to do is I'm actually going to work through part 2 of the lab with you. Your job is to kind of follow along with part 2, and then you're going to be able to do part 1 in the lab. Or if you are virtual, you will be able to get some makeup data and kind of work through the calculations. So I'm just looking at the procedure. It says transfer 50 milliliters of 1.00 molar hydrochloric acid to the calorimeter. Here's my calorimeter. Again, styrofoam cups, very insulated. I'm going to take my 1.00 molar hydrochloric acid. It says 50 milliliters. So I'm going to measure 50 milliliters. Now, it does not have to be exactly 50 milliliters, but it does need to be whatever you write down it is. Okay, so make sure carefully, once you measure your 50 milliliters, if you get down to eye level, you can always pick this up also, get down to eye level. I think it's about 49.8 milliliters. So we're going to record 49.8 milliliters. Okay. And then it says measure 0.35 milliliters. Oh, before I do that, I do need to actually measure the temperature of the solution like it says. So I'm going to take my 49.8 milliliters. I'm going to put it in my calorimeter, and then I'm going to go ahead. I've got my temperature probe set up with Logger Pro, and I'm going to put my thermometer down in there. And this really should be at room temperature, so it should also be giving me what the thermometer was also reading. But I look here, and what I'm seeing on my computer, it says 19.4 is my initial temperature of the solution. So I'm going to record that in the data table, 19.4 degrees Celsius as my initial temperature. We don't know the final temperature yet, so we're going to kind of hold that thought there. All right, now I'm ready for step 2. Measure 0.35 grams of magnesium oxide. Magnesium oxide is like a white powder. So I'm going to put my weigh boat on the balance, and then I'm going to measure as close as I can. It does not have to be exactly 0.35, but I want it to be pretty close. And then whatever it turned out to be is actually what I'm going to write down. So it looks like I'm at about, see if I can get it right on, 0.35. So 0.35 grams, that's our mass of magnesium oxide, 0.35 grams. Then it says transfer the magnesium oxide to the hydrochloric acid solution in the calorimeter. Then I'm going to put the lid on, and I'm going to rotate, and I can actually probably just stir with the thermometer. So here's what I'm doing. I'm taking all of this magnesium oxide. I'm going to quickly put it in my calorimeter, and then I'm going to put the temperature probe down in there. And what I'm going to do is just kind of keep an eye on my temperature on my computer, and I can actually tell the temperature is going up. Right now I'm at 19.9, 20.0, and I'm going to keep doing this until I get the final or highest temperature that I'm going to reach. So I'm at 20.5 right now, and I'm just going to kind of keep stirring, keep swirling. I'm at 20.7, 20.8. What's happening right now? This reaction of magnesium oxide with hydrochloric acid is producing heat into the surroundings, right? So this reaction is actually an exothermic reaction. We'll get to that in a minute. And we're because of that, we're seeing the temperature of the surroundings go up. I'm at 21.7 right now, and I'm going to keep stirring and keep stirring, 21.8. I'm at 22.0. Goal here is to hit that highest temperature, 22.1, 22.2, 22.3, 22.4. So we're just going to keep going until temperature doesn't go up anymore. I'm at 22.5. 22.6, and as long as it doesn't go up anymore, once it's very steady or even potentially goes back down, I'm at 22.7, then I will stop and record that as my final temperature. 22.8. And it does say on here that it could take up to 3 minutes. Hopefully it's not going to take us a full 3 minutes to get that temperature, but 22.8, 22.9. And if you were to look in here, you can see most of it's pretty well dissolved. I'm at 23.0. All right, I'm gonna call it 23.0 is my final temperature, and that's what I'm gonna record on my data table, and I will go through and work all these calculations with you so you can kind of see what is happening for this lab. All right, hello College Chem. Today we're going to talk about Lab 6.3, and here's the process. I'm actually going to work through part 2 for you, and I've already done a little bit of showing you what that process looks like. So if you would follow along in the lab and write down, record part 2 of the calculations. So here we are on part 2. Let me flip to the second page. And again, I've already kind of gone through the procedure with you, and I have some data recorded. So let me go ahead and kind of write these numbers in, and then we're going to kind of walk through the calculations. So my volume of HCl that I had recorded was 49.8 milliliters, right? The final temperature, I ended up at 23.0 degrees Celsius. I started in the calorimeter at 19.4 degrees Celsius, which means my temperature change, remember you do time T final minus T initial to get my delta T. So I end up with a positive 3.6 degree temperature change. The mass of my magnesium oxide was right at 0.350, and this is for MgO, okay? All right, so here's first thing we're doing. We're gonna write a balanced molecular and net ionic equation. Some of you could probably use the review on this one. So we are adding magnesium oxide, which is a solid, to hydrochloric acid, which is a solution. And in the process, you may have a little trouble with this. This is going to end up making magnesium chloride, which is a solution, and H2O, which is a liquid. We're not going to spend a lot of time on how come or why in terms of this reaction. That's why I'm doing part 2 with you. I think part 1 is going to be a little easier for reaction. But this metal oxide and acid together actually make water and, in this case, magnesium chloride, which is a salt. We go through the process to balance. You put a 2 in front of HCl. Magnesium looks okay, oxygen looks okay, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. So now it is balanced. Remember, we do not break up solids, so our MgO, magnesium oxide, stays intact. However, our strong acid, HCl, does break up. And on the other side, magnesium chloride would also break up. So we're going to end up having our 2 hydrogen, but our chlorines actually go away. They're spectators. On the right side over here, we have Mg2+, which is aqueous. And then we do have water still. Remember, it's a liquid, don't break it up. Is this reaction endo or exothermic? It is exo. How do we know it's exo? Because the temperature of the thermometer increased. Remember, the thermometer is always part of the surroundings. So since the surroundings temperature went up, the system must have been given off energy, right? All right, so we're going to take this information and then I'm going to move on. I'm going to kind of have to clear this, and that way I can kind of scroll down on the next part. And we are going to walk through this process. We kind of have already done this on the handout with 6.5, but I want to make sure this process, whoops, go back to page 2. I want to make sure this process makes sense to you. And so here we go. It says, since the solution is mostly water, assume the density is 1 gram per milliliter. Also assume the specific heat of the solution is 4.184 joules per gram degree Celsius. Calculate the change in enthalpy heat of the reaction. We're going to use this Q equals MC delta T equation again. The mass has to do with the solution. And since I put in 49.8 milliliters, and since we see here that we're assuming the density is 1, we're going to just use it as 49.8 grams as our mass. Specific heat, we're supposed to use this 4.184 joules per gram degree Celsius. And then if you think about our temperature change was a positive 3.6 degrees Celsius. We plug this into a calculator. The calculator is going to give us 750, we're going 2 sig figs, joules of energy, right? However, from the perspective of the reaction, it's actually Q equals negative 750 joules, right? Because water absorbed, water would be positive, or solution was absorbing energy. But from the perspective of the reaction, it's actually negative 750 joules, okay? All right, then the next step of the process, we're going to take our 0.35 grams of MgO, and we want to convert that to moles. So get rid of grams of MgO, go to moles of MgO. And then what I'm going to do is I'm going to calculate molar mass. Magnesium is 24.31, and then we have 16 for our oxygen, so that's 40.31 grams per mole. When I punch this into a calculator, I get 0.0087 moles of magnesium oxide, okay? Now, this is the important part. It says determine the molar heat of reaction by dividing the heat of reaction from number 3 by the number of moles of magnesium in number 4. Your answer must be in kilojoules per mole. So here's what we're going to do. If you go back to question 3, I wrote negative 750. So our negative 750 joules, we need to convert that from joules to kilojoules by dividing by 1,000, right? So we're going to call this negative 0.75 kilojoules. Then what we're going to do is we're going to divide it by the number of moles that we just calculated for magnesium oxide, which is 0.0087 moles of MgO. When you punch this into a calculator, negative 0.75 kilojoules divided by 0.0087, you end up 2 sig figs, negative 86 kilojoules per mole. So based on magnesium oxide, that is how much energy is released per mole of magnesium oxide, right? Okay, so we write that number down, and here's what I'm going to do. I've got to move on to the next page. So I'm going to move to page 3, and there is a spot for this. If you look closely here, reaction 2 is the second line. So what I do is I take my experimental value of negative 86 and I put it here. By the way, the reaction, in case you were curious, was already written on this next page here. So this is part 2 of the lab we just did. You are going to do part 1 in class, and you're going to get this delta H value. When you are finished, I've actually given you a third reaction here with the delta H. You are going to go through and use Hess's law and take these 3 equations and manipulate them, put them together for this overall reaction. And once you figure out how these 3 reactions fit together, remember all you do is whatever you do to the reaction, do to that to the delta H, and then sum them up, and you're finding the delta H of this overall reaction. That's really our goal in this lab. Once you do that, there is a question down below where you're going to find the amount of error, percent error in this lab that we have done. You will find percent error based on the theoretical value. So good luck, and let us know if you have any questions.